Good evening. Welcome back to the module Communication Theory, Learning Outcome 1. In the previous session, we studied about the condition for Wide stationary random process. Uh, the condition for the wide stationary random process is that if the random process is stationary to the first order and if the random process is stationary to the second order, then the given random process is called a wide stationary random process. In that, the Weiss's in that the stationarity in the first order the random process is checked by finding the distribution function of the given random process or by finding the mean value of the given random process. The mean value is constant, then we can say that it is stationary to the first order. Similarly, the stationary to the second order of the random process will be calculated by finding the joint distribution function of the given random process or by calculating the autocorrelation function. If the autocorrelation function of the random process is depend only on the time difference of the given random process T1 and T2, then the given random process is stationary to the second order. Okay, if these two conditions are satisfied, then the given random process is called a wide stationary random process. In communication system, we are studying that the given the received signals are wide stationary random signals. All the received signals are we assuming that it is a wide stationary random process, which means that it is satisfying the mean value is constant and then the autocorrelation function depends only on the time difference of the given random process. But it does not depend on the observation time of the given random process. Okay, that's why we are telling the received signal in the communication systems are wide stationary random signal. Okay, and we studied some properties of the autocorrelation function of the random process. Okay, at tau equal to 0, so we are modeling that the time difference is T2 minus T1 by the delay tau. So if tau equal to 0, we can get the mean square value of the given random process. That is the first property of the autocorrelation function. And the second property is that at a tau equal to 0, the autocorrelation function giving the maximum amplitude or the magnitude of the autocorrelation function is maximum only at the tau equal to 0. So that is the second property of the autocorrelation function. And the third property of the autocorrelation function is that the autocorrelation function satisfying the even condition. It is an even function, which means that RV of tau equal to RV of minus tau. After that, we studied about the ergodic process. Okay, the ergodic process normally we are studying in the communication system. Example for the ergodic random process, the sinusoidal signal. Okay, the randomly phased sinusoidal signal is the example for the ergodic random process. Uh, and we can check the condition for the ergodic process by checking the mean value of the given random process and the mean square value of the given data process. If these two parameters, that is mean and the mean square value of the given random process is constant, then that process is ergodic random process. So today's session we are going to discuss the few more points in the stationary random process, and then some example for the stationary random process, like the random digital waves, and then Gaussian process, then how to find out the power spectrum from the given random process. We can recap some of the points from the previous session. A random process is ergodic if all time averages of the sample functions equal to the corresponding ensemble averages. Okay, so this is a very important point or a condition to check the given random process is ergodic random process. which means that the sample function, we have to find out the time average of the sample function. So the time average of the sample function is equal to the ensemble average of the random process. Then the given random process is called exotic random process, because each of the random process is having the n number of sample functions. Okay, so for each sample function we can calculate the time average. Okay, that time average of the single sample function is equal to the ensemble average of the random process. Here the ensemble average means we are averaging all the sample functions. By averaging all the sample function, we are getting that mean value. Or by averaging one sample function, by time averaging one sample function, we are getting that average value. Both are equal. If both are equal, then that kind of random process is called the exotic random process, which means that the all ensemble average of an exotic process are independent of time. Okay, so it irrespective of time, the average value is it is maintaining the constant average value or constant mean value. The ergodic process maintaining the constant mean value irrespective of the time of occurrence of the event. Example, the randomly phased sinusoidal signal. And we can check the condition for the ergodic process, that the mean and the mean square value of the random process is constant. So expectation of the random process v of t equal to v bar into the expectation of v squared of t. So which means that mean of the square of the random process, mean of the square of the random process. That's the mean square value, which is equal to v squared bar. So this v bar is the mean of the random process. V squared bar is the mean square value of the random process. So here the mean square value equal to the variance plus the mean of the given square of the mean of the random process, or we can say that mean squared value of the random process, sigma v squared plus me squared. And in ensemble random process, okay, in ensemble process, we are using some notation. So this notation indicate the average of the ensemble. Okay, this notation indicates the average of the ensemble vi of t. So vi of t means the I varies from 1 to 1 to n. There are n sample functions. By averaging these n sample functions, it will be equal to expectation of the random function v of t. Okay, if it is independent of time, if the given random process is independent of time, then we can say that the average of the ensemble equal to expectation of the v of t. Similarly, another notation here we can see that the average of the square of the ensemble, average of the square of the ensemble. Here, average of the ensemble, average of the square of the ensemble, which is equal to the expectation of the v squared of t. This is the mean square value of the random process. This is the mean of the random process. And then the mean value equal to the DC component, that is the average of the ensemble. This notation, this cross product notation indicates the ensemble of the random process. And the mean squared, mv squared means mean squared, which is equal to the DC component, DC power. Okay, then the mean square value v squared bar equal to the total average power. So this is actually the total average power, that the average of the square of the ensemble, and then the variance sigma v squared equal to the AC power. And the sigma v is the standard deviation of the random process, which is equal to the RMS value of the time average component. So the stationary process, we already studied that stationary process. There are basically the random process are divided into two type of stationarity. One is the Wildstone stationary. So while the condition for the Wildstone stationary means it should be the random process should be stationary to the first order. That is expression of v of t equal to mv, and the random process is stationary to the second order. That means the autocorrelation function which is equal to RV of T2 minus T1. That is depend only on the time difference T2 minus T1. If these two conditions are satisfied, then the given random process is wide and stationary random process. And another type of random process is strictly stationary random process. So for strictly stationary random process, we need to check the nth order joint distribution function with the time shifting, okay, which is equal to the nth order joint distribution function without time shifting. If it is satisfied, then the random process is called a strictly stationary random process, which means that for any number of random process, any number of random processes, uh, the average value does not depend on the time. So that in that case, we can say that the given random process is a strictly stationary random process. It is totally independent of the occurrence of the time. So any ergodic process satisfy above conditions, or we can say that that random process is wide and stationary random process, and an ergodic process is strictly stationary, which means all ensemble averages are independent of time. Okay, if it is independent of time, then it is a strictly stationary. Okay, then so by checking these two conditions, we can say that the given ergodic process is wide and stationary. And further, if it is independent of time, the ensemble average are independent of time, then we can see that it is strictly stationary. And we can note down that all the stationary processes are necessarily not necessarily a ergodic process. Okay, some of the stationary processes not ergodic. Okay, and here you can observe that the autocorrelation function of the ergodic process are analogous to the autocorrelation function of the deterministic signals. So this is a very important things. Okay. So for ergodic type of random process, the autocorrelation function is analogous to the autocorrelation function of the deterministic signal. Then the average power of the random process V of t will be equal to the ensemble average of the average of the square of the random process. Okay. So the P asymptotically equal to expectation of the square of the ensemble. Okay. So expectation of the v squared of t. Here the only difference is the first term indicate the it's the ensemble average of the random process. It is independent of time. The expectation, the way you are putting the expectation inside this inner product means it is independent of time, the given random process, so that both are equal. We are saying that the both terms are equal. It give the average power of the random process V of t. So actually, that random process is ensemble random process. If because we are telling that all the ensemble functions are independent of time, so we can finding the average power of the ensemble average of the average power of the ensemble process. Okay, by calculating the average power of the normal random process. Because here we are not mentioning that I. Okay, subscript I. If subscript I is means that is the ensemble process. Okay, so here actually you can see here the power is the average power is calculated from the ensemble. So here we are using the subscript I, which means that there are n number of sample functions. By averaging square of the sample function, we are getting the average power of the ergodic process. So which is equal to the mean square value of the ergodic process, that is v squared bar. And so here we should note down this difference. Here how we are here we are not using that subscript I, but here we are using that subscript I for the ergodic process. Okay, which means that we are averaging the square of the ensemble to find out the average power. Then the ergodic process having the mean square. This is the mean square value of the random process. So expectation of v squared of t. okay, which is equal to that average of the square of the ensemble. This is the this inner product indicate the ensemble. Okay, average of the ensemble. Because of the square, we have to tell that average of the square of the ensemble, which is equal to the mean square value of the given random process. If it is independent of time, the given random process, ergodic random process is independent of time, we can equate both terms. The ensemble average is equal to the average of the random process. Okay, and this vi squared is replaced by v squared of t. Okay, so that we are telling that the mean square value of the random process, ergodic random process, equal to the expectation of v squared of t. Okay, so here we have to note down the notation we are using the for averaging of the random ergodic random process and averaging of the ensemble random process. Okay, if the process is stationary means, but it is not necessarily ergodic. So in that case, we can find out the mean square value. Mean square value of the stationary random process, that is expectation of v squared of t, which is equal to rv of 0. So that is the autocorrelation function at a tau equal to 0. So the average power, the mean square value will be equal to average power of the random process, which is equal to the rv of 0. Because at rv of 0, the autocorrelation function having the maximum magnitude. All stationary process of the practical interest having the autocorrelation function, the magnitude of the autocorrelation function is greater than 0. Hence, the most of the sample functions are power signals rather than the finite energy signals. Another important point about the stationary random process. Okay, so all the practical stationary random process whose autocorrelation function magnitude is greater than 0. It is a positive value, so that the sample functions which is observed in practical scenario is the power signal, not the finite energy signal. Now we'll discuss with one example to understand about the ergodic process of the given random process. Now take the ensemble from the rectangular pulse train. I can see you can take randomly on the rectangular pulse train. Okay, so we are telling it is an ensemble random process, and so you have to consider some parameter like the all pulses having that fixed and non-random duration. So here capital D indicate the duration of the pulse. It is not a random, it is a the constant one. It's a fixed duration D. And but it that rectangular pulse train is having the two random variable. One is the delay. The delay TD is a continuous model as a continuous random variable, and it follows the uniform distribution. Okay, uniform distribution over the interval 0 to d. That is the one random variable in this rectangular pulse train. And another random variable which is lying in this rectangular pulse train is amplitude. The amplitude of the rectangular pulse train also is random. Okay, that is AK of the kth pulse. For every pulse, the amplitude of the rectangular pulse trains are random in nature, and it is modeled as a discrete random variable with mean expectation of AK equal to 0 and the variance is sigma square. Then the amplitude in different intervals are statistically independent. So in this rectangular pulse train, amplitude in the different intervals are statistically independent. So it is checked by this mathematical representation, that is expectation of AJ and AK. AJ means the jth amplitude in the jth pulse duration. AK means amplitude in the kth pulse duration. So it is a auto correlation. It is a cross correlation of these two amplitudes of the pulses. So because of both are statistically independent, so we can equate the which is equal to the product of the expectation of the individual amplitude pulses. That is expectation of aj into expectation of ak, which is equal to 0. Okay, and the kth pulse duration. So we can see here the diagram for the, like this is the random digital pulses or random digital waves. You can see here the x-axis is the time of the pulses, and the y-axis is the magnitude or amplitude of the pulses. We can see here that duration of the pulses are constant. It is not random. The D, capital D, is the duration of the pulses. It is the constant one. But the random in this digital waves are lying in the two parameter. One is the delay. Okay, the delay TD is a random nature. Okay, every time the delay is varying, and another parameter is amplitude of the pulses is also random nature. This delay is modeled as a continuous random variable, and the amplitude of this rectangular pulse train also random nature. So here the A naught one amplitude, A2 is another amplitude, A3 is another amplitude. So it is modeled as a random and discrete random variable, right? So in this and the rectangular pulse train, they having the two the random variable. One is the delay and the another one is the amplitude. And the duration of the one pulse is varies from kd plus td to k plus 1 d plus td. Okay, where td is the delay of the pulse and the capital T is the duration of the pulse. So the mean value of the amplitude, the expectation of V of t equal to expectation of ak, means the kth pulse amplitude will be equal to 0. Means the mean value of the amplitude is 0, and the expectation of b squared of t. Okay, but the variance of the amplitude equal to sigma squared. Okay, the expectation of ak squared equal to sigma squared. So being independent of time, these results suggest a stationary process. Okay. So this is the waveform representation of the random digital waves. So now our target is we have to check whether the given the random digital waves are wide stationary or not. Okay. So how to check? We have to check the stationarity in the first order and the stationarity in the second order. To test the wide and stationarity, so already we checked that the mean value. So the mean value is 0 for the pulse amplitude. Expectation of AK equal to 0. This is the stationarity in the first order, and we need to check the stationarity in the second order. So that we have to take the time t1 and t2. If the t1 and t2 are in different intervals, right? And the t1 means the interval of the first pulse, t2 is the interval of the second pulse. The difference between these two intervals means that t2 minus t1 is greater than d. Okay, so which means that the duration t2 is larger compared to the duration t1. So in that case, the autocorrelation of this random process, that is expectation of v of t1 and v of t2 equal to expectation of aj and ak. Here we are checking only that the second we are checking that autocorrelation function for the amplitude of the pulses. Okay, we are not considering the delay time delay of the random rectangular pulses. Okay, so that the expectation of v of t t2 equal to expectation of aj ak, so which is equal to 0 because the amplitudes are statistically independent. Okay, so that it will be equal to 0 when t2 minus t1 is greater than d. Or if and the modulus means both the negative and the positive sides we are checking. So if t2 minus t1 is less than d, okay, when it becomes less than t means if that duration t1 and t2 are in the adjacent intervals or in the same intervals, right? If T1, T2 are in adjacent intervals or in the same intervals, then the modulus of T2 minus T1 is less than capital D duration. Okay. So in that case, the autocorrelation function, that is expectation of V of T1, V of T2 equal to 0 when T1 and T2 are in the adjacent intervals. Or the expectation V of T1, V of T2 equal to sigma squared, that is the variance of the given random process, if the T1 and the T2 are in the same intervals. If it is same interval, it will give the variance sigma squared. Right? Now we can consider as a event that V of T1 as a event, okay? So which is occurring when the T1, T2 are in the different intervals. The different interval means the difference is greater than D. The same intervals means the difference is less than D, right? So that the total, if you model as a event, okay, then the expectation of the V of T1 and the T2, V of T2, if we can add both condition. If the T1, T2 is greater than D, what is the autocorrelation function? If the T1, T2 less than D, what is the autocorrelation function? If T1 minus T2 is greater than D, means the expectation of AJ and AK, because two different amplitude into the corresponding probability P of A, that is the probability of the event A. Here the event is in the T1, T2 is greater than D, plus the expectation of AK squared into 1 minus P of A. So the second time is the T1, T2 is less than D. So the T1, T2 less than D means 1 minus P of A. T1, T2 greater than D means P of A. That's the probability of the particular event. There are two events here we are considering. Since that amplitude of these randomly digital waves are statistically independent, so this term will be zero. The expectation of AK equal to zero. But in second term, the expectation of AK squared is the variance sigma squared 1 minus P of A. If T2 minus T1 is less than D, so assume that the probability of the event A, P of A involves the random delay. So here we are considering that random delay to find out the probability of the event A, okay, as well as in the T1 and the T2. Now, if you take the condition, if T1 is less than T2, then the P of A equal to that interval. You have to consider the probability of the event which is lying in between T1 and the T2. So assume K equal to 0 means the delay is lying in between T1 and the T2. So in that case, the probability of the event is calculated by integrating. It is like that averaging the delay. Okay, delay tt. So the limit is varies from t1 minus kt to t2 minus kt, and because of the delay is uniformly distributed, so it will be 1 by t. It is varying from 0 to d, so that it is 1 by t. That is the PDF function for the delay, and we have to differentiate tt. After we have to integrate. So after integrating, we are getting that probability of the event P of A equal to T2 minus T1 by capital T. So we are getting that P of A. Similarly, here we considering T1 is less than T2. If T2 is less than T1, also we are going to get, but the sign will be different. T1 minus T2 divided by T will be get. We are getting. So that we can take the finally the PFA equal to modulus of T2 minus T1 divided by D. Now we can replace replace that P of A in that autocorrelation function, that is expectation of V of T1 and V of T2 equal to sigma squared of 1 minus, now substitute here this way P of A modulus of T2 minus T1 by D when T2 minus T1 is less than T. So finally, we are getting the for random digital waves autocorrelation function. When T2 minus T1 less than T, we are having the autocorrelation function which is equal to sigma squared of 1 minus T2 minus T1 by D. And if the interval T2 minus T1 is greater than D means autocorrelation function is 0. So finally, the observation for this random digital waves is that since the autocorrelation function depends only on the time difference T2 and T1 and T2, then the random digital waves follows the Weissen's stationary. So we can say that the given random digital wave is Weissen's stationary random process. So that is the observation from this analysis. And we can replace that t in autocorrelation function. There is a t2 minus t1. That is the time difference, okay, of the observation time. So we can replace that t1 and t1 minus t2 by tau. Then the correlation function becomes rv of tau equal to sigma squared gamma of tau by d. Okay, we are modeling this term as a some other function t2 minus t1 by d. We are modeling as a triangle function. Okay, so by varying the tau, we can get this waveform triangle waveform. That's why we are telling it's a triangle function, and it have the maximum magnitude at a tau equal to 0. That is sigma squared. Okay, so at a tau equal to 0, we are getting that average power of these random digital waves. That is p equal to sigma squared, or variance of the random digital waves. Normally, we are telling that variance of the random process is sigma squared. Okay, actually, that variance of the random process is average power of the given random process, which is calculated from the autocorrelation function at a tau equal to 0. And but this random digital waves not ergodic. Okay, so we can say that the average power, this sigma squared of the sample function, is differ from the means the average power of the sample function is differ from this power value, the average power of the process, random process. So this average power is calculated from the autocorrelation function. Okay, so this is actually ensemble average. It is differ from the average power of the sample function, because it is not the ergodic random process. If it is ergodic, means both values are equal. The average power of the sample function is equal to this. The average power of this the process, that is p equal to rb of 0 equal to sigma square. And one more example, instead of only one random process, now consider the two random process is added together. It is modeled as z of t1 comma t2, the time t1 and the time t2. We are observing the two random process at the time t1 and t2, and modeled as a one random process, that is z of t1 and t2, which is equal to v of t1 plus or minus v of t2. Then by using this fact, the expectation of the square of the random process is greater than or equal to 0. Then you have to check this condition, that is the modulus of the autocorrelation function is less than or equal to rb of 0, because the rb of 0 is the maximum magnitude of the autocorrelation function. Now we can find the mean value for the given random process. Actually, this is the sum of two random processes. Z is sum of two random processes at a time t1 and t2. So take the expectation of the given random process. We have to substitute the z function. That is v of t1 plus v of t2. And then because of okay, because of this random process v of t1 and v of t2, okay, added together, we have to apply the expectation separately. So we can rewrite this equation like expectation of v of t1 plus expectation of v of t2. So the expectation of v of t1 equal to mean of the random process at the time t1. So that is mp. It is independent of time. Similarly, the expectation of v of t2 also mp. So mb plus me equal to 2me. So this is the mean value for the given random process. And we can find out the autocorrelation for this random process, that is r z of t1 comma t2. Already in the given random process is observed in two different time, right? Okay, so that we have to take that random process and square without changing the time. We can observe. Okay, so the expectation of z squared of t1 t2, substitute that z function that is V of T1 plus or minus V of T2. It is looking like a plus B whole square formula or A minus B whole square formula. Expand by using A plus B whole square. So we are getting the expectation of V squared of T1 plus expectation of V squared of T2 plus 2AB. So 2 into expectation of V of T1, T2. And okay. So here we can see here the expectation of V squared of T is a mean square value, variance of the random process. So sigma square. So V squared expectation of V squared of T2 is again sigma square, and expectation of V of T1 is mean value. So MB squared. So 2 MB squared. So here 2 sigma square, 2 MB square, 2 is common, take outside. So therefore autocorrelation function is 2 into sigma square plus MB square. So therefore, the autocorrelation function of the given random process is set of T1, T2 equal to so 2 into sigma square plus MB squared into 1 minus T2 minus T1 by D. If the T2 minus T1 is less than D, same like with the previous example, the randomly digital base, and 0 if T2 minus T1 is greater than D. And again, we can replace that difference, time difference T2 minus T1 by tau. So we can get the autocorrelation function R V of tau equal to 2 sigma squared ME squared plus ME squared into that triangle function, that is gamma tau by D. And at a tau equal to 0, we are getting that maximum magnitude, that is 2 into sigma squared plus ME squared. This is the maximum value, so that the condition is satisfied. The modulus of the autocorrelation function is less than or equal to RV of 0. Then the next topic, Gaussian random process. Okay, so this is most of the received signals we in communication system. We are using this Gaussian random process to get the some statistical information of the received signal, like a mean and the variance of the given the received signal, right? So here the random process is called a Gaussian process if all marginal, joint, and conditional PDF of the random variable Pi are Gaussian functions. Okay, so this is the condition for the random process is a Gaussian random process. Okay, then the important properties of the Gaussian process, it has the four properties. The first property of the Gaussian random process is that the process is completely described by the mean and autocorrelation of the random process, and that is expectation of V of t and RV of t2, t1, comma t2. And then the second property of the Gaussian random process is that if RV of t1, comma t2, that is the autocorrelation function, equal to expectation of V of t1 into expectation of V of t2, which means that the autocorrelation function of the random process is the product of the mean of the individual random process at a time t1 and t2. So that the random process V of T1 and T2 are uncorrelated and statistically independent random process. Then the third property, if V of T satisfy the condition for wide distance stationary, then the process is also called as strictly stationary and ergodic random process. This is a very important property, third one, because if the Gaussian process is wide distance stationary process, means we can say it is a strictly stationary random process also. And also we can say it is a ergodic random process. Then the fourth property, any linear operation in V of t, that is a random process V of t, produces the another Gaussian random process. Okay, the linear operation means adding the two random process, that is V1 of t plus V2 of t. Again, it becomes the Gaussian random process. So these are the properties of the Gaussian random process. We'll see one example for the Gaussian random process. Okay, by considering the autocorrelation function. Okay, here they given the random process W of t, which is equal to 2V of t minus 8. Here the V of t is the Gaussian random process, whose mean equal to 0, and the autocorrelation function equal to 9 e power minus 5 modulus of t1 minus t2. So now find the mean value. So expression of W of t equal to substitute that W of t equal to 2 V of t minus 8. So since 8 is constant, so we can take the expectation for the random variable V of t. So 2 into expectation of V of t minus 8. So since we know that expectation of V of t equal to 0, it is given in the problem, we are getting the mean value equal to minus 8. So constant only it is coming as a mean value. So why we are getting minus 8 means when taking the expectation for the constant, it is remaining, it will be same value we are getting. So that's why the expectation of W of t equal to minus 8. Then the autocorrelation function of the random process. Okay, so we can find out by taking the expectation of the random process W at a time t1 and time t2. That is expectation of W of t1 and W of t2. Substitute that function W of t 2v at t minus 8 and then multiply. We are getting that 4 terms. Okay, and now we can put time t1 equal to t2. So it becomes the 4 into expectation of v squared of t1 minus 16 into expectation of v of t1 minus 16 into expectation of v of t2 plus 64. And we know that the expectation of the v of t equal to 0. That is mean value of the random process, Gaussian random process is 0. So second and the third term becomes 0. This is constant, it is coming, but the first time is the mean square value of the random process. So it will be equal to that autocorrelation function, that 9 e power minus 5 t2 t1 minus t2, right? So that 9 into 4 equal to 36 e power minus 5 t2 minus t1. You have to substitute here. Plus 64. So this is the autocorrelation function for the given random process. Yes. Even we can simplify here at a t1 equal to t2, that exponential term also going to be 0. So 36 plus 64 equal to 100. So finally we are getting 100 as a the autocorrelation function. Here I forgot to simplify that term, substituting that t1. Okay. Then the Poisson random process. Poisson random process, this Poisson random process is another type of random process which depend on the random randomness of the time division multiplexing of the channel, the communication channel. Okay, the variation of time division multiplexing for random access to a channel is called alloga. We can call it as a alloga. So alloga means the variation of the time division multiplexing for the accessing the channel is called alloga. Okay, because the channel will be accessed by the many users with the different time. Okay, so that we are calling it as a alloga. It is modeled as a random process by using Poisson distribution. That's why we are telling the accessing the channel in the communication system modeled as a Poisson random process, or we can call it as a alloga. Okay. A channel with the multiple users sending the data packets of length, the packet length is t at various times and independent of one to other. Okay, so each users are sending different time. So, okay, then there are three steps for sending the packet in the communication channel. The step one, a user will send the packet to some destination regardless of other users existing users on the channels. So without knowing the other users are present or not, the user can automatically, after receiving the packets, the user automatically send the packet into the destination through the communication channel. Then the step two, if the transmission is not acknowledged by the destination, then it is assumed that the packet will be lost because of collision with one or more packets sent by other users on the channels. Okay, that's the step two. Then the step 3, the sender retransmit the packet until it is finally acknowledged. Okay, so this is the algorithm for the Aloga data transmission in the network. Then the time frame for the collision is considered the 2T duration. Then the packets arriving at some point can be modeled as a Poisson process because the arrival of the packets at some particular point is also a random nature. Sometimes it may be two packets will be arrived, sometimes it may be 10 packets, sometimes it may be a 15 packets, and so on. So we can model as a Poisson random process. So here we are using that one parameter, that is the pocket rate. It is indicated by mu. Here the mu means it's not the mean of the random process, it's the pocket rate of the random process, which means the number of packets arrived at a particular number of packets received at per second. That is the meaning of pocket rate. Now you can consider there are I packets are sending during the interval of 2T. Then the probability of the I packets colliding during that interval 2T. So it is modeled by using Poisson random process. This is the Poisson random formula for the Poisson distribution function, that is P of I means I packets expectation of minus mu 2T into minus mu 2T power I divided by I factorial. This is a Poisson distribution formula for the check the probability of the I packets collision during the interval 2T. Then what is the probability for the no collision? So the means the packet will be successfully transmitted. Okay, not successfully transmitted, no collision. Then the probability of no collision equal to expectation of minus mu 2T. Where mu is the number of packets per second. Then probability of packets being successfully received. The probability of packets being successfully received equal to the mu into e power minus mu into 2T. So that is the difference between the probability of no collision, the probability of successfully received. And the each, you can see here the last point, the each user on the channel would be synchronized. So all packets transmission is done at a specific times. Okay, this modification is called slotted aloga, because in the previous normal aloga, each users are sending randomly without knowing is there any other users are existing in the channel, so that there is a collision. But in slotted aloga, the each users are synchronized, which means the user should know at what time he should send the packet during in the channel, so that the collision will be avoided. So this kind of transmission is called slotted Alaga transmission. Then coming to the last topic in today's session is power spectrum estimation. So by applying the theorem, Weiner-Kinchi theorem, we can find out the power spectrum for the random process. It will be calculated by taking the Fourier transform of the autocorrelation function. Okay. So the power spectrum of the random process V of t will be calculated by taking the Fourier transform of the autocorrelation function, and the power spectrum is the distribution of the average power P over the frequency domain. Okay. So then the formula for the power spectrum is GV of F, where V means the random process, given random process V of t. So GV of a power spectrum of the random process by taking Fourier transform of the autocorrelation function. That is F of RV of t, RV of tau, which is equal to the formula for the Fourier transform minus infinity to plus infinity RV of tau e power minus j2 pi f tau into d tau. And conversely, by taking inverse Fourier transform of the power spectrum, we can able to estimate the autocorrelation function of the random process, that is RB of tau. So both are reverse to each other. So from autocorrelation function, we can find out the power spectrum, and from the power spectrum, we can find out the autocorrelation function by applying the Fourier transform and the inverse Fourier transform respectively. So we can call that autocorrelation and power spectral density of the random process is the Fourier transform pair. And some of the properties of the power spectrum is the first property, the integration minus infinity to plus infinity GV of t of df equal to RV of 0. So that means the integration of the power spectrum okay, over the interval minus infinity to plus infinity will be equal to the mean square value of the random process or average power of the random process P. Okay. Then the second property is the power spectrum of the random process is always greater than or equal to 0. Then the third property, the power spectrum is an even function. That means GV of minus f equal to GV of plus f. So, so here this is the representation how we are finding the power spectrum from the autocorrelation function. So already we got this expression from the randomly phased sinusoid. The autocorrelation function for the randomly phased sinusoid is a squared by 2 cos 2 pi f naught tau. So by using this autocorrelation function, we can able to find out what is the power spectrum, so which is equal to a square by 4 del of f minus f naught plus a square by 4 del of f plus f naught. We'll see the derivation how we are getting the power spectrum for this randomly phased sinusoid. So we have to substitute the autocorrelation function and then taking the Fourier transform of the autocorrelation function. Okay, that is a square by 2 minus infinity plus infinity cos 2 pi f naught tau e power minus j 2 pi f tau into d tau. And we know that cos theta formula e power j theta plus e power minus j theta divided by 2. We have to replace this cos function by that by using that Euler identity and take the 2 outside, so it becomes a square by 4. Then we can combine the exponential term within this bracket. So we can write like e power j 2 pi f naught minus f into tau plus e power minus 2 pi f naught plus f into tau into d tau. So by combining that e power minus 2 pi f t f tau with that inner bracket exponential term, we are getting this term. The one is the difference, one is the sum of the frequency component, one is the difference of the frequency component. And after integrating, we are getting this term. Okay, and by substituting the upper and the lower limit, okay, we can see here it becomes e power j theta minus e power minus j theta divided by 2j. So this e power j theta, here theta means 2 pi f naught minus f into t, right? So e power j theta minus e power minus j theta divided by 2j equal to sin theta. So that's why here we are replacing up after substituting upper and lower limits. It becomes sin of pi f naught minus f into t divided by pi f naught minus f into t, right? F naught into f only. But similarly for the second term, after substituting, we are getting the sine function. Now you can see here it is looking like a sine function, sinc function, sine pi x by pi x. Because of in denominator there is no t, we need to multiply both numerator denominator by t. Okay, so that the value does not change, and then we can modify this expression like a sinc function. That's why here we are multiplying both numerator denominator by t, capital T. That is the duration of the pulse. Okay, so it is now looking like a sine pi x divided by pi x. So we can replace this term by the sinc function. So sinc of f naught minus f into t plus sinc of f naught plus f into t into a squared by a squared t by 4. That's the power spectrum. Now at f equal to f naught, you can consider f equal to f naught. So what has happened? F equal to f naught, it becomes sine 0. So at sinc 0, so at sinc of 0, the sinc function having that maximum value. So maximum value is occurring at 0. The f naught minus f equal to 0, we are getting the maximum value. So that is 1 by t into del of f naught minus f. Similarly, at f equal to minus f naught, the sinc function is giving the maximum value. Okay, only at 0, the sinc of 0, it is having maximum value. So that we can replace this sinc function by the delta function. So 1 by t, capital T into del of f naught plus f. So therefore, finally, the power spectrum of the given random process is Gb of f equal to a squared by 4 del of f naught minus f plus del of f naught plus f. Okay, thank you. So today's session we discussed the three important topic like in the random digital waves and some more points in this stationary random process. Then we discussed about the how to find out the power spectrum of the given random process, and then what do you mean by Gaussian random process. Okay, what are the properties of the Gaussian random process? Thank you.